Hi friends, welcome back to my YouTube channel. In this video, we are going to study another type of round robin arbiter. As you remember, in previous video, we studied about fixed time slice round robin arbiter. So where the time allocated to every requester to access a shared resource is fixed. For example, let's say that every requester is able to access the shared resource for 4 clock cycles. So what happens is in fixed time slice round robin arbiter, since the time slice is fixed, so for example a particular requester is only required to access the shared resource for 2 clock cycles. So here, out of 4 clock cycles, the requester will utilize 2 clock cycles, but the remaining 2 clock cycles are basically getting wasted. So to avoid that, or basically to save the time, we are going to introduce, or we are going to design another type of round robin arbiter, which is variable time slice round robin arbiter. So let's get started. So as we have already discussed in our previous video of round robin arbiter designs, we are basically going to skip some of the points here, like what is an arbiter, the applications and examples of the arbiter, advantage, disadvantage. So these basically we have already discussed in our previous video of round robin arbiter designs. So in this video, let's start directly the Verilog HDL design. Let's synthesize the designs, simulate it and analyze the waveforms. So before that, let's go for the specifications of this arbiter which we are going to design in this video. So the arbiter is, again, it will take the 4 requests and it will output a single grant signal in the form of 1 hot. The round robin scheduling algorithm is going to be the same as we discussed in our previous video. The extra thing here is every requester is going to get 4 clock cycles. But if the requester is not using its 4 clock cycles, there is a mechanism such that the arbiter can grant the second requester. That means if a particular requester is only using the shared resource, for example 2 clock cycles, then the arbiter will basically grant the next requester for the remaining 2 clock cycles, and hence saving the time. So now let's go to the EDA playground, and in EDA playgrounds I have already coded the designs, the HDL designs. So let's walk through this design. So as you can see, the arbiter is going to have the 4 input signals, clock, reset and 4 request, and 1 output grant signal. So here we are basically going to use a counter which will basically count from 0 to 3. So basically we are using basically this counter for allocating 4 clock cycles to each and every requester. Then we will have our present state, next state register variables defined, and here we are defining 5 states through which the state machine of the round robin arbiter will go through. So here is the first procedural block, which is a sequential procedural block. So here on reset, the present state will get the idle state. So in the idle state, the arbiter will be in the idle state on reset. So once it is in a reset, the arbiter is in reset, the state will be idle state. Once the arbiter is in out of reset state, the present state will basically get the next state value. Now let's see how we can implement this next state logic. So the next state logic is a purely combinational block, where once the present state is idle state, so once the arbiter is out of reset, it is going to be in the idle state initially, and when the present state is idle state and the arbiter is out of reset, we will start sampling the request input signals. So if the request 0 is asserted, the next state will be S0. Else, if request 1 is asserted, the next state will be S1. Else, if request 2 is asserted, the next state will be S2. Else, if request 3 is asserted, the next state will be S3. Now, once the arbiter comes out of the idle state, it means that it is one of the S0, S1, S2 or S3 state based on the input request. So suppose when the arbiter is in the S0 state, that means if the arbiter is in the S0 state, that means the request 0 has occurred. The requester first is trying to access the shared resource. So here, as per the specification of this round robin designs, we are saying that every requester should get 4 clock cycles. That means if the requester 0 is, or the request 0 is high for 4 clock cycles, the arbiter is going to be in the S0 state only. So how to make sure, how to write the HDL code for this condition is, if the request 0, so when the arbiter is in the S0 state, that means the request 0 has occurred. So when we are in the S0 state, we are again going to sample the request 0. If the request 0 is still asserted, and if count is not equal to 2 tick B10, basically we are counting from 0, 1, 2. So when the count reaches 2 tick B10, that means the arbiter is in the S0 state for 4 clock cycles. So let's be clear here why we are using the count value 2 tick B10. So the counter is counting from 0, 1 and 2. So basically when the arbiter has some transitions from one another state to S0 state, it consumes that 1 clock cycles. So for that 1 clock cycles also the arbiter in S0 state, then in S0 state again the arbiter is going to be in the S0 state for 3 more clock cycles. So counting total 4 clock cycles in S0 state. So when the counter reaches 2 tick B10, that means the arbiter is in S0 state for 4 clock cycles. And here we will see, we will sample the next request, which is request 1, and the counter we will reset the counter, and next state we will go to S1 state. Else if request 2, then S2 state, if we request 3, then S3 state, else count 0 and next state becomes S0. That means if counter is not equal to 2 tick B10, or when the counter has not reached the value 2 tick B10, till then it is going to be in the S0 state only. Else keep incrementing the counter by 1 and be in the S0 state itself. So this else is corresponding to the count value 2 tick B00, and this else is corresponding to request 0. Now what happens is the arbiter came into the S0 state when the request 0 is asserted, and after one clock cycles, suppose in the next clock cycles the request 1 is dropped, the request 0th request is dropped, and then if the 0th request is dropped, then we are not going to waste the 3 clock cycles in S0 state itself, because the requester 1 has already dropped its request. So we are going to give the remaining 3 clock cycles to the next requester. So here we will see that else if request 1 is asserted in the next clock cycles, then we will reset the counter and we will go to the S1 state. If request 2 is asserted, we will go to the S2 and as well reset the counter. If request 3 is asserted, we will go to the S3 state and we will reset the counter. Else if, let's go to the idle state if none of the request is asserted. Likewise, the same logic for S1 state. Then we have for the S2 state and S3 state. Now let's see the output logic. So here we are saying that we want a registered output, which is always a glitch-free output. So for a registered output, basically the output should go through a register. So for that we have to implement a sequential always block. So here on reset, anyway we are resetting the registers, that means the ground signal will become 0 0. Else, based on the present state, if the present state is as 0, the ground will be 0 0 0 1. If as 1, the ground will be 0 0 1 0, and so on. If you want to try this code out, please write in the comment sections and I can share this code with you. First we are going to synthesize this design. So to synthesize these designs, we are going to use the Yosis synthesis tool, and we will check in the show diagram after run. Now let's save these designs and run it. So this diagram is going to be pretty big, but I want to show you some portion of this diagram which is important to analyze. So let's see, where is the output ground signal. Okay, so here is our ground signals, and you can see the ground signal is basically the D flip-flop register output. So this is a registered output. What are the advantages of registered outputs? We will be covering it in next one of our video. Now let's simulate this design. So I have written the test bench already. We will go through the test. We will try to understand it. So these are the inputs. This is the output. Here we have the DUT instantiation. Here we have the clock generated clock. We are basically generating a 10 nanosecond clock. Here we will initialize the DUT. So basically in starting the reset is deasserted. Then after some time we are asserting the reset, and then we will be deasserting the reset. Then we will driving the request signals randomly, and we will finish the simulations after some time. This below code is for dumping the signals in the waveform window. Now let's select the simulation tool, which we will be using LDEC Rivera. Don't forget to check in this open EPWave after run, and save the designs and run it. So here are the signals. Let me rearrange them. So in this waveform window, actually all the signals, internal signals as well, are getting dumped. So we will see the important signals here. Let's change the radix to binary as well. So if you see here, when the arbiter comes out of the reset here, and the next rising edge of the clock happens here. So before that, on falling edge, the request, so let's call 0th, 1st, 2nd and 3rd request. So the request 3rd has asserted. So once the request 3rd has asserted, here there is one important point to note that the 3rd request is asserted here and the rising edge happens here. But the grant to the request 3rd is happening at the next clock cycles here. So why this is happening? Why the grant 3rd didn't happen at this clock edge? This is because the registered output. The grant is a registered signal. So just try to understand how this is happening. If you have any doubts on this, please write down in the comment section and I will try to explain it in more details. So once the 3rd request is asserted here, the 3rd request is granted at this clock edge. At this clock edge as well, the 3rd request is still asserted. So in this clock edge as well, the 3rd request will be granted, still be in the grant state. At this falling edge, the 3rd request has dropped. The 3rd request, once the 3rd request gets dropped, the next number comes is for request 0, then request 1, then request 2. So if you see here, the request 0 is also not asserted, request 1 is asserted. So when the request 1 is asserted, then at this clock edge, basically the request 1 is asserted here. So when the request 1 is asserted here, at this clock edge, the request 3rd was still asserted. So in this clock edge as well, the request 3rd will be still in grant state. Just remember that here there is a latency of 1 clock cycles. This latency of 1 clock cycle is coming because of the registered output. So if you want more details on this, how it is happening, please write in the comment section if you have any doubts. So if you see here, the request 0 is the first request is asserted here, but now the first request is and the 3rd request has dropped here. So if the 3rd request has dropped, then the number will come to the next number will be request 0, then request 1 and request 2. If the request 3rd would have still be asserted, then it would have granted, the arbiter would have granted the access to the 3rd request itself only, because ideally we are allocating 4 clock cycles to each requester. But since here the request 3 has dropped, so the next requester here is the requester 1. So the requester 1 has asserted here and it will be granted the access here. Now in this clock cycle as well, the requester 1 is still asserted. So here also the requester 1 only will be in the grant state. Here as well the requester 1 is still asserted, and here as well the requester 1 is still asserted. So the requester 1 is asserted for 4 clock cycles and it will get the 4 clock cycles to access the said resource. Here the requester 1 has dropped its request, and requester 2 is basically requesting the said resource access. So that will be granted in the next clock cycles. Now if you see here, at this clock edge, the requester 2 has dropped and the request 0 is asserted. Once the request 0 is asserted, the next clock cycles, the requester 0th is granted. And here the requester 0 has again dropped and request 1 is coming. So in the next clock cycle, the request 1 will be asserted. So the point to note here is, if a request is getting asserted for 4 or more clock cycles, then it will get access for the 4 clock cycles. Otherwise, it will be only granted access for the requested clock cycles only, or for the clock cycles during which the request is asserted. Hope this is clear to you. If you have any queries, please write down in the comment sections. If you like this video, please hit the like button. Also, please do subscribe this channel and enable the notification so that you will get notified as soon as I upload a new concept on digital design. Thank you very much.